Python to optimize a trebuchet. And it might seem, well, why would one want to do that? Let me discuss. First, my name is Charles McCreary. I'm an engineer in Northeast Texas. And I've been using Python for a number of different things from and related to my engineering work since I think it's 2.0 something. And we use Python primarily for scientific and engineering type applications, some back office type. Yes? Oh, it is? F11? Is that better? I think it's still clipping, isn't it? How about not full screen and kind of, oh, you hit an F11 to get full screen. What do you hit to get out of full screen? F11? There we go. How about move it over until it no longer clips? Is that better? Can we go any further, or is that about the limit? Okay. Back office type applications, interfacing, parsing tickets from a pipeline, locating, call before you dig, putting it into the database, Django web apps for traditional type of web applications. But mainly I'm a structural engineer, stress, thermal analysis, fluid flow type work. The kind of projects that we've been involved with over the years, offshore wind turbine foundations. This is a particular foundation that's going in the North Sea that was installed last year. It was a metrology mast in which they measure wind speed, wave heights, and things like that, designed for about 100 meters of water depth. This is the jacket structure that sits about, the bottom of it sits about halfway in the water column. LED lighting. This is a LED fixture that I designed, a prototype made out of machined aluminum. It's a max of 4 watts. That produces the equivalent of about 180 watts of an equivalent incandescent of 180 watts. That guy in the background also is the fellow that invented the optical mouse. Hoover Diana, top side. Here's a photograph. Every one of those joints we analyzed to determine what the fatigue life of that would be. This is offshore from Corpus Christi. I believe at the time, this is about 10 years ago, they spent about $1.6 billion on that platform. We do a lot of offshore structures work, both wind generator and oil and gas. Snack foods. Who would have thought, right? In fact, my wife says when somebody asks, what do you do? She says, start and stop with potato chips, okay? Because people just really get bored otherwise. You'd be amazed at how much engineering Frito-Lay puts into their products and how they make their products. Take, for instance, the Stax product. They thought, if Pringles can do it, Procter & Gamble isn't even a snack food company, certainly Frito-Lay can do it. They found out there's a lot to it. And everything from the design of the fryer and making sure that you don't exceed the critical speed of the oil so you don't have standing waves in the oil that you're frying them in, to making sure that all the chips don't get trapped in the edges. Because when they get trapped in the edges, they overfry and turn brown, and those are the brown chips you pull out of the bag that you don't like, right? And so if you notice, Frito-Lay, they very rarely have brown chips in their bags because they very carefully engineer the fryers using me and computational fluid dynamics code and a lot of Python to make sure that the flow stays rather regular. In this particular case, we have a Stax container that they initially wanted to differentiate themselves from the cylindrical Pringles can, so they came up with an elliptical cross section. But of course, when they put the hot chip in there and then they vacuum seal it, what happens? It shrinks. Well, an elliptical shape is a poor pressure vessel, especially for a vacuum. So what we ended up doing is putting this marketing feature in the top and the bottom to stiffen it so it wouldn't crush all the chips as soon as you sealed it, which is what we found when we first sealed them. But what do these have to do with Python? Well, for one, significant data processing. I first used it for scripting my finite element software, and then continued on from there. Parameterization, so if you need to run thousands and thousands of optimization runs, you're not going to do it by hand. Generating reports. My delivery to my customer is typically a PDF file that they would include as an attachment to their client, or perhaps they are the end client. So I use this in generating LaTeX tables and figures and such like that, so that if it's a project that I do over and over and over again, most of it is scripted. Also, building analysis tools. A lot of the simulations we do don't require massive horsepower, but you have to do a lot of them, and they can be done very easily in Python. Now, engineering notebooks. Actually, you can call it a lab book, an engineering notebook, whatever. But if as an engineer you have a lot of calculations, those calculations need to be documented. Oftentimes you include them in the report that you send to your client. If you're a scientist or a biologist or whatever, you would have your lab notebook that you record everything with. So what I have used in the past are tools being like MathCAD and Mathematica. Now, I like Mathematica a lot. It's a very good tool. I barely tolerate MathCAD, especially because what they charge for and what I get compared to other tools. And I was really looking for a replacement. Why a Trebuchet? Well, what I was trying to do was, after SciPy in Austin, actually the last two SciPys, this IPython notebook. I was like, man, this is really pretty neat. You know, you can include mathematical equations in there. Got to do that. You can include figures and plots and interactive graphics. You can keep it under source code version control. What a concept, you know? And so I said, well, I'm going to have to learn this sufficiently so that that's my go-to tool rather than Mathematica or MathCAD. And I needed a project to do that. Hence, optimizing a Trebuchet. Now, the second reason is it'd be a lot of fun because I'm going to build this Trebuchet. We're going to sling stuff in the pasture until we, run out of pumpkins to chunk. I've never built one before, so I thought it'd be a fun project. Now, as some of you may know, Trebuchet is a medieval siege weapon, and it combines two ancient weapons, the traction catapult and the sling. You know, the sling like David slew Goliath with, right? And it's typically a beam mounted on an axle with a heavy counterweight, sometimes called a counterpoise catapult. And the counterweight's on the short end, and then on the long end is attached a sling. And essentially, it's a triple pendulum. The hinge at the counterweight, pendulum and beam, and the rest of it's kind of flowing off of it. Hinge at the axle, and then I think I can make this a little bit smaller, bring it up. No, I can't even do that. A hinge at the sling and the beam. In other words, you have an axle in the center, a counterweight arm, and then at the end of the long end of the beam, you attach a sling. And here, I think, is a picture of modern replicants, if you will, of these medieval siege weapons that were used to sling boulders until you completely demolished the fortress you were laying siege to. But it's not just medieval. This is a photo from the Arizona border that was taken a few months ago in which drug smugglers were using this, I might add, poorly designed trebuchet, but sufficiently effective to sling bales of marijuana over that fence. And so they could do that, never cross the fence, and they could deliver it to their mules on the other side. So it's still being used, right? Now, mechanics of a trebuchet. Of course, I'm a lazy person, and I'm not going to sit down and I'm derive this because I started to do it using Newtonian mechanics, and it just got really tough, and I had work to do to get paid for. So I would recommend these two sources here: Modern Siege Weapons, Mechanics of the Trebuchet, and another one called the Algorithmic Beauty of the Trebuchet. Unfortunately, they're rather light on details. And I might add that all of this math I'm going to show you and delight you with is in my public GitHub repository that you cannot even see there. Let's see if I can bring this up just a wee bit. Can we see it now? No? Let me shrink it just a little bit. There we go. Okay. So you can go to this GitHub, github.com, McCreary, trebuchet-optimization.git. You can clone that and have all these fine IPython notebooks, and off you go. So basically, you can look at it. You can break it down into parts. You can initially look at what's called a seesaw pendulum, right? You've got this great big mass on one end, and you've got your projectile mass on the other, and you have some fulcrum point, right? What's going to happen? It's going to do this, right? Now, you further idealize that. This is actually not, this is a terribly inefficient design. An improvement on that design would be what's called a hinged counterweight, in which the counterweight has got its own arm and it's hinged up there. So now its action is more uniform. It's a lot more efficient design. And notice that in the previous slide, how many degrees of freedom do we have in this system? One. There's 1 degree of freedom, and that's the angle theta, right? All we're solving for is theta and theta dot. Theta dot being the angular velocity there. Well, when you introduce the hinged counterweight, you have 2 degrees of freedom, right? Theta and phi. In other words, the angle is made with the hinged counterweight makes with the main arm. And then when we introduce the final element of it, we have now 3 degrees of freedom. We have the 2 previous, theta and phi, but we also have the angle between the sling and the arm. Now, a sling is really a rope, right? And it's flexible and all that. But if you're slinging a mass on the end of it, we can make the approximation that that sling is really an inextensible massless rod. The beam is massless. The only masses we have are the projectile mass and the counterweight mass. Those are kind of huge simplifications because the structure itself does have mass associated with it. But here's the tool chain. Python, obviously. SymPy for the computer algebra and computer calculus that we use and that I use also in my day-to-day work. IPython for the IPython notebook. Who here uses IPython and IPython notebook? Outstanding tool, especially the latest the latest branch. I think it's what, 0.14, is that right? What we're at right now? I always call it NumPy, but everybody else calls it NumPy, okay? Travis Oliphant over at Inthought, tremendous work in wrapping high-performance numerical, the basic linear algebra system, or BLAS, LAPAC, which is what, linear algebra, blah, 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 but those 2 things have always been used. Unless you were using Fortran, you couldn't use them. But with NumPy, you can. And then built on top of NumPy is a fantastic collection of tools called SciPy that has things that we will be using, such as optimization, as well as a lot of other things like Kelvin functions and lots of obscure transformations that you never think you need to use until you use them. Now, who here uses the Flask micro framework? Okay. What's your templating engine, right, of choice? Jinja 2, right? Those of you familiar with Django have used the Django's templating engine, very similar. So what I do, if I have to do these optimization routines, I have a finite element template. And within it, I use Jinja 2 to stuff everything into it by just rendering that template with the variables that I want as a dictionary. It works fantastic. And here we've done it for the optimization of the Trebuchet. Anybody use PYX or PIX for data plotting? Anybody even heard of it? Okay. Have you ever seen those really nice plots in your scientific journals? You can do it straight in with Python. I mean, it's similar to Matplotlib, but easier. And I use this general purpose finite element analysis program. It's my bread and butter. It's called Abacus. I actually learned how to use it here at A&M way back when. Hey, who here are Aggies anyway? We got any Aggies in the room? There we go. My middle daughter just got her ring yesterday. Stand up, Becca. Come on, there you go. Show us your ring. There we go. There we go. She was afraid I was going to do that. Now, let's go straight into this. We have the mechanics of the seesaw model. So one way we can do the seesaw model is, and we saw this picture here earlier, is this is the IPython notebook. And anybody recognize this is kind of the newish look to it, right? But I think it's not so new now, but it was to me. Now the engineer kind of way to step into it would be using something called Newtonian mechanics to sum all the forces and all the accelerations, and it gets very tedious very fast. And so a faster way is something called the Euler-Lagrange equation, which is shown right here. Where basically we're looking at some little bit of variational calculus here, and we're minimizing the difference between the potential and the difference between the kinetic and the potential energy. So it's a variational calculus type problem. And lo and behold, we can do it in IPython notebook. We define these symbols. Is this the canes? No. Okay, we define some reference frames so we can use vectors. We define the kinetic energy of the system. We tell it to simplify it. It prints it out in a form I like to see. It's basically a LaTeX. It's rendered using MathJax. Nice. So I'm already happy. The potential energy of the system, it's a little more complicated. We simplify it. Bingo. All we got to do is solve that nonlinear differential equation. Okay, piece of cake. Well, there's one thing about it, though, is using the Euler-Lagrange starts to get kind of unwieldy. So there is a means of doing this called Keynes method. Somewhere, I would hold up my textbook here showing dynamics, an old textbook. Anyway, Keynes method is a nice way of solving multivariable dynamics problems. It's less unwieldy than Euler-Lagrange, but as you will see in a little bit, it can generate some awfully complicated equations. Anyway, and using the Euler-Lagrange, we come up with this differential equation. But using Keynes method, we define, we got our variables. L1, that's the length of the counterweight arm. L2, the length of the projectile arm. Notice how this is, if we look at the actual code for this is a display equation that should be oriented, that inbox should be oriented to the left, but for some reason MathJax is oriented to the right. We can just kind of take that as it is and run with it. But you can see that you can typeset a lot of stuff in here using typical LaTeX math. And so we define our symbols here, our masses, our gravity. We define a reference frame at the axle. We create an axis normal to the plane at the axle. I won't go through a lot of these details. But using Keynes method, we come up with, bingo, a system of differential equations of two variables. We have one variable is theta, our angle, and the other one is theta dot, right, our angular velocity. So what would be nice if I said, oh, great, that's in SymPy, that's symbolic. I'd like to just shove it into my numerical solver from SciPy that I use from the SciPy module, the ordinary differential equation integration. But I can't, because I need to print that out in Python code from SymPy, and code printing doesn't really work for going to Python. It actually works for going to Fortran and C, but I can't take it and generate the Python code because I need to shove it into this right-hand side, right? So what I do is I cut and paste. So I cut and paste theta v, and here. Okay, well, that's not too bad. That's just a little bit, right? And then I give it the parameters. I give it the initial conditions. The initial conditions would be theta would be 3 pi 4, right? It's tilted at an angle of 45 degrees. Fire that, let it integrate it, and lo and behold, I get answers for theta and theta v. And let's go ahead and we hadn't run it yet, so we have no plots. Earlier when I tried to run it on there, sometimes the plot didn't show up, even though I had PyLab inline. Notice how the kernel is busy, it's integrating, it's doing all this magical stuff, and no plot. Oh well. We'll go to a little bit, stay on this page. I'll go ahead and save it. Let's go ahead and jump to the hinged counterweight sling using Keynes method. Now, this is the problem we're actually trying to solve, right? We don't have any constraints on that mass. Obviously, on a real trebuchet, you'd be slinging it, and that mass would be riding on some kind of track, and then it would come around and then go off. But here we're just... For a real design, it's going to be pulling it so hard it's not going to sink below the track that would be there. So let's first see if we can run this thing. This actually takes a little bit because, as you will see, there's a lot of math. Remember the two equations we came up with? Well, how many degrees of freedom do we have now? We have the axle, that's theta. We have the angle between the counterweight arm and the beam, that's phi, and then psi would be the angle between the beam and the sling. So it's 3 degrees of freedom. So we have 3 variables plus their velocity, so that's a total of 6. Now, see what I mean about cutting and pasting? So what I have done is I printed out the the derivative portion of it, that is a lot of sines and cosines, right? But I go ahead and I cut and paste it. Notice how the slide bar can go a long way to the right, right? So I have these 3 degrees of freedom. Here I'm calling them U1, U2, and U3. And then the other 3. So these are basically a system of differential equations with a total of 6 equations. And let's see if it, for some reason when you have it hooked up here, it doesn't like to do the plots. But we'll see if, oh, it did it. Okay, so here we have plots of our 3 variables over time. I let it run for 1 second. The time step was 0.005. I didn't really check whether that was numerically stable or sufficient. It probably wasn't, but you know, it'll work for our purposes here. And then more interesting is a plot of the velocities. Now, anybody heard of a double pendulum problem? Okay. What's kind of weird about a double pendulum? What can it do? Or even a triple pendulum? Be chaotic, right? It can be a chaotic system. Well, as I found while doing a lot of these, depending on my parameter combinations, I would have a chaotic Trebuchet, which was its plot. You know, you develop your own Poincaré map on this, but it would be kind of a large thing to experiment with. So the experiment I thought was a great success because I was able to do really everything I needed in the IPython notebook, with the exception of feeding in the symbolic results to the numerical solver. Because if you use the numerical solver in SymPy, it's just horribly slow. Whereas this is, of course, using probably Runge-Kutta or some other much more efficient solver. So that limitation there, as long as you're aware of it, it works really well. I really like how the IPython notebook coupled with SymPy works. Now, I couldn't just stop there. Okay, I was done with what I set out to do. But I needed to optimize this using the full power of my $25,000 a year plus finite element software, and this is what we did. Okay, now to optimize it, we're going to be using SciPy. And SciPy has, as I mentioned, these SciPy.optimize has all these optimizations. Now typically when you do optimization, you expect a Jacobian, right? A matrix of the changes of your variables. I don't have a Jacobian, okay? All I'm doing is I have some parameters, I shove it in, I get answers, right? So what I have is a black box that I feed it parameters, and I have an objective function. What's my objective function? What am I trying to maximize or minimize? I'm trying to maximize the range. I want to chunk that as far as I can, right? So we all know that 45 degrees is the perfect place for it to launch. And when would it launch? Now, typically a trebuchet would have, that sling would be on a hook, right? A straight hook. So as you're slinging it out, once it became collinear, boom, your projectile would launch. And it would go, then obey Newtonian mechanics and fly in its line until it lands. And so that's our objective function, is to maximize the range. Or in the case of, if you can only minimize something, multiply it by -1, right? If you're trying to minimize something, you just multiply your positive objective function by -1. Now, so the most appropriate nonlinear multivariate optimization that you can use is Kobi-La, which is constrained optimization by linear approximation. That's in the SciPy toolkit. There's 1 or 2 others. I just couldn't get them to work as well as I'd really hoped. And I've done this before. And here's how I do it. This just as an aside. Let's say you have parameters that vary greatly in scale. Like, for example, my counterweight was like 260 kilograms. My counterweight arm might be, say, 0.08 meters, right? Those vary a lot, but the Kobi-La is just using the same kind of tolerance on those parameters as it's using for everything. It's not using a relative tolerance. And there's another thing. Let's say you need to introduce kind of an artificial constraint without a constraint function. You can use this logistic function, which looks like this, to say, first feed it into the logistic function, which says that no matter how big, negatively, or how small or how big the parameter is, it's constrained to be between 0 and 1. So it's sort of an artificial clamping on the ends of your parameters. And so all of your parameters would be in the range of 0 to 1 because you're first feeding it into this logistic transform. And it's a neat little trick. I think I forget where I learned it, but it was very useful in this case. Since I planned to build this eventually, this trebuchet, I needed to constrain the size. I mean, obviously, I could throw something a long, long way. Like, there's an old show called Northern Exposure, a TV show, and it started with an opening sequence of a grand piano flying through the air. They launched that with a trebuchet. Now, I'm thinking, okay, hold on a second. Typical rule of thumb, the counterweight mass is typically 1,000 times the mass of the projectile. How much does a grand piano weigh? How big was that actual trebuchet to launch a grand piano? And how many takes did they have to do? And how many grand pianos did they have to go through, right? I don't have that kind of cash. I'm going to limit it to, my trebuchet arm is 1 meter long. And I'm going to try to throw an orange or a small pumpkin, approximately 0.2 kilograms, right? Now, we could put a larger, like watermelon in there, but it's not going to throw it as far. I furthermore have constraints that obviously the masses and all the lengths must be more than 0, right? Now, I mentioned that you assume the projectile release occurs when the sling and the beam are collinear, approximately. That's approximately true. And that this will occur at some angle theta from the horizontal. And this is also the tangential velocity vector from horizontal is also this theta. It works out to be the same. And so what do we have? We have, from your Physics 101 course, projectile motion that a high school physics student can solve, which is this equation for your range. So the sequence is this. We have this program called Trebuchet optimize.py. I think I have it. I may have it open. I may not. Well, we're going to, since Wingware is one of our sponsors, we're going to use Wingware IDE to look at the code. Otherwise, you'll be watching me use VI. We have, let's see. No, this is a Django project, so we're going to close all this out. And we're going to open up our Trebuchet, aptly named. Okay, this is the Trebuchet optimize. And so we load up the template that we're going to use. And this is the Abacus input file. And so we use Jinja 2 to render that template. So we create the template object. And then we have the parameter list here, x init. Here's our projectile range function. And our dictionary of converting it from the length to x and y. We render the template. We open the input file. We write it. We close it. We use subprocess to call Abacus. We run it interactively, because normally it would just spawn it off. And then furthermore, we run another program called projectile range that extracts out our objective variable. I think, yeah, here it is. And basically, this just calculates, based on the results from the model, it calculates the angle, the velocities, and everything that's going on. And then here I just write out a file and then reads the file. You could use 0MQ or some other kind of cool way of transferring that data. But once you're done, then you start a new run, right? And also keep track of how the solution is progressing. Now, as a result, here is the Abacus simulation. And what's moving here is the projectile. There's the counterweight. And notice when it gets to about 45 degrees, what happens? It goes back because of the influence of the projectile. Now, any motion past that, notice how the projectile doesn't actually leave. I'm not interested. Once it hits that collinear mark, I'm done, okay? What it does after that, I don't really care. But when I was looking at some of these simulations of interesting combinations, I noticed some just behaved wildly, chaotically, and I thought, oh yeah, double pendulum, chaos, that's right. And notice how you can embed, raw HTML, in this case, a YouTube video, straight into your IPython notebook. Just as an aside, if you're ever going to do that, use the old embed method, not the new one, because the new one puts it in a frame, and as you step through your slides, it's still there, showing it. So use the old one if you're going to do it. Now, here are the. Well, that's no good. It's trimming it for me. Let's open up the raw PDF. Trebuchet, of course. That's where it's always been. Actually, that would be in here. AVI. Nope, be in docs. Optimization results. Okay. So remember I was mentioning something called PYX for plotting? This is a kind of graph that you can generate. Multiple y-axis. That's a pain in the rear to do a Matplotlib. And you can do a Matplotlib with like 2 axes, but anything else you're really going to have to monkey patch the heck out of it. And so what we have is the evolution of the variables as the optimization progressed. Now keep in mind I cheated on this because I kind of knew where to start. So I didn't use unreasonable values, and I used values that were fairly close. But notice how the range kind of varies wildly until about the 5th or 6th increment, and then it starts, okay, I know where to go now, right? We have the, if we remember, L1 is the length of that counterweight arm between the axis and where the counterweight hangs from. And that is a black line, or blue line actually, and it corresponds to about 0.08 meters, which is, what, about that far, right? Well, that's barely enough for me to put a bearing in a bearing, right? But it's close enough, right? The counterweight mass, notice how I kind of cheated, see where I started at? I kind of knew it needs to be about 1,000 times larger, 0.2. That gives it about 200 kilograms. And it turns out to be that the optimum mass is about, let's see, mass is red, 210 kilograms, right? And so all the rest of it kind of settles down, and so that gives me an optimum, or when I say optimum, what do I mean by optimum? Well, it's what the optimization algorithm coughed up, right? But just what does that mean in terms of efficiency? Well, we could say that the ultimate measure of efficiency would be converting all of the potential energy of the counterweight into kinetic energy of the projectile, right? And if I use that, this is 46.6% efficient. Well, not bad, right? But really, you'd be more interested in what's called range efficiency. So knowing that at 45 degrees, that's the optimum release angle from, if it starts like this, you want it to end up like that, because 45 degrees would give you the longest range, right? So you would say for the highest velocity that you get, what would be the longest possible range, and then compare the range you get to the optimum range. And in that case, if you do that calculation, this actually comes out to be 81% efficient, which is about as good as you're ever going to get, especially for a medieval weapon, right? So anyway, that was the experiment that I ran, and the objective of the experiment was to really learn and validate this tool chain of primarily IPython, SymPy, and PYX and Matplotlib for replacing what I have been using, which is MathCAD and Mathematica. And hopefully what I'll do is I'll take this, we'll build one, and then present it at SciPy or PyCon perhaps in March and July. Any questions? Anybody want videos of the eventual trebuchet? Raise your hand. Yeah. Thanks.